Okay, hello Math 122 and welcome to the first video that I will be producing for the class. So today we're going to be talking about section 4.1 on local extrema, in particular local maxima and minima. So let's get started. So just some review from some topics that have been covered in chapter 2. There is a nice relationship between derivatives of a function and the slope of the function as well as its concavity. So let's go through those relationships first. So first off, if the derivative of the function is greater than 0 on an interval, then it implies that the function itself is increasing. So if I draw a little picture, it means that the function looks something like this. It's going up. If f prime is less than 0 on an interval, then f is decreasing. If f double prime, so the second derivative, is greater than 0 on an interval, then f is concave up. So here the function looks something like this, like a bowl. And if f double prime is less than 0 on an interval, then f is concave down. So the function looks something like this, an upside down bowl. Okay, so let's use this information to look at a function and calculate its derivative and figure out some of the behavior of the function. So in the first example, f of x is x cubed minus 9x squared minus 48x plus 52. And the goal is to determine when f is increasing, decreasing, and when the derivative is equal to 0. So the first thing we're going to do is take the derivative of the function. And we get 3x squared minus 18x minus 48. And we're going to take this derivative and set it equal to 0. And now we want to solve for x to figure out when f prime is equal to 0. So the first thing I notice is that I can take a factor of 3 out of here. And I get this resulting expression. And now I can take this x squared minus 6x minus 16 and factor it. So I'll factor that as an x minus 8 times x plus 2, still equal to 0. And this implies that x is either equal to 8 or x is equal to negative 2. So these are the two places where the derivative is equal to 0. And this answers one part of the question. So to answer the other part of the question, we have to make a little bit of an observation. And that observation is that if the derivative is going to change from positive to negative at some point, then there has to be a point in between where it's positive and negative where the derivative is equal to 0. So what we're going to do is we're going to draw a number line, and we're going to put our 2 points where the derivative was equal to 0 that we just found. So we have x equals negative 2, we have x equals 8, we're putting them on the line here. And the question is the derivative positive or negative at each of these points, or at each of these intervals around these points negative 2 and 8? And so we'll figure that out by picking test points from each of those intervals. So to the left of negative 2, I can pick the point negative 3, for example, and there's tons of different points that you could choose, but I'll choose negative 3. And if I take negative 3 and plug it into the derivative, I end up getting (3 times negative 3 squared minus 18 times negative 3 minus 48. And if you calculate this out, you find out that this is bigger than 0. So over with this left question mark, we're going to replace that with a positive. So to the left of negative 2, the derivative is going to be positive, which means that our function is increasing to the left of negative 2. Okay, and how about the interval between negative 2 and 8? So to test for this interval, I'm going to take 0, because that's 1 point between negative 2 and 8, and plug it into the derivative. And here I get a minus 48, which is less than 0. So in the middle interval, the derivative is going to be negative. So the function is decreasing. And finally, I can pick a test point to the right of 8, say 9. And if you plug this in, you again get something that's bigger than 0. So the derivative is positive to the right of 8. So we say that the function is increasing to the right of 8. So this is the game that we're going to play over and over again when we're looking to find where our function is increasing or decreasing. We find all the points where the derivative is equal to 0, and then we pick test points from the intervals around those points to figure out whether the derivative is positive or negative on those intervals. Okay, next example, now relating the second derivative to the concavity of the function. Let's see if we can determine when f is concave up by looking at the second derivative. So we have the first derivative given to us, and the second derivative is going to be 6x minus 18. And remember, when the second derivative is positive, our function is concave up, and when the second derivative is negative, our function is concave down. So we want to determine when is the second derivative positive and when is it negative. And to do that, we're going to set the second derivative equal to 0 first. So 6x minus 18 equals 0 implies that x equals 3. And then we're going to play this game with the number line again. So we draw a number line, we take that point x equals 3 and put it on the number line, and now again we make the same observation. So if the second derivative is going to change from positive to negative or from negative to positive, it's going to have to be 0 somewhere in between. So we can pick test points to the left of x equals 3 and to the right of x equals 3 to determine if the second derivative is positive or negative on that entire section of the number line. So we'll take f double prime of 2. So this will give us a point to the left of x equals 3. And if we plug this in, we get 6 times 2 minus 18. This is less than 0. So the second derivative is going to be negative to the left of x equals 3. And now we'll take a test point to the right of x equals 3. So 4 will work here. And we get 6 times 4 minus 18. And this is going to be greater than 0. So the second derivative is positive to the right of x equals 3. So what this means is that f is concave down to the left of x equals 3. So I'll write that in here, concave down. And it is concave up to the right of x equals 3. Okay, and we can use this information to sketch a graph of this function f. Okay, so going back to the previous slide, we had 2 points where f prime was equal to 0. That was at x equals negative 2 and x equals 8. And so I'll make special note of those points. And I'm going to find output values for both of those points. But I'm first going to make note of the point x equals 3 as well. And we'll find output values for the 3 of them. So the output value for 8 in our function is negative 396. The output value for negative 2 is 104. And the output value for 3 is negative 146. So you can find each of these 3 values just by taking the x values and plugging them back into the original function. And now I'm going to plot those points on the graph, or at least give like a rough approximation of where they should be. So f of 8 is negative 396, so we get a point somewhere down there. F of negative 2 is 104, so maybe I'll put a point here. And f of 3 is negative 146, so I'll put a point maybe about here, just kind of approximating here. Okay, and now we want to draw a function that goes through these 3 points. But I have some additional information. So if you go back to the previous slide, I know that f is increasing to the left of negative 2. So I'm going to draw something like this, And I know that f prime has to be 0 at -2. So my function kind of has to level out there. And now my function is decreasing to the right of -2. And I know that concavity is going to change at x equals 3. And I know that f prime is 0 again at x equals 8. And now I'm increasing to the right of x equals 8. So the information that we ascertained from playing this game with the number line before and both of the derivatives, it allows us to graph our function, or at least give a pretty good sketch of what the function looks like. Okay, so this was kind of an informal introduction to the topics for this chapter. So I'll give you a definition of what a local extremum is. First off, f has a local minimum at a point P if f of P is less than or equal to the values of f for all of the points near P. So this is really just a fancy way of saying that the point f of P is kind of the bottom of a valley on the graph. So if you look down at the graph I have at the bottom with our example, this local minimum is occurring at the very bottom of the valley of that graph there. A local maximum, on the other hand, is going to be a point at the top of a hill on our graph. So technically, this is a point P where f of P is greater than or equal to the values of f for all of the points that are right around P, very close to P. And if P is either a local minimum or a local maximum, then we would say that P is a local extremum. So local extremum is just a word encompassing both. And the trick to finding these local extremum or extrema is by finding critical points. So that's the game that we play. And a critical point, so here's a definition for you. A critical point is just a point P where the derivative is going to be equal to 0 or the derivative is undefined. So if either of these things happen, then we say that our point is a critical point. So if we go back to the previous slide, this is why we were taking the derivative functions, both the first and second derivative, and setting them equal to 0. We set the first derivative equal to 0. That's because we're finding critical points. And finding these critical points ends up being important to finding the local minimum and the local maximums. Okay, so locate the critical points of the following functions. Well, I already located the only critical point for the first function. The critical point for the second function is just, again, either the top of the hill on your function or the bottom of the valley of your function. All the points where the slope is equal to 0. Okay, so the first derivative test, this is the first time where we're going to use critical points to tell us how to find local minimum and local maximum. So the first derivative test tells us that if I have a point, and it's a critical point of my function f, and I'm moving from left to right, so that'll make sense in a second. If the first derivative changes from negative to positive at the point P, then f has a local minimum at that point P. And the second possibility, if f prime changes from positive to negative instead at the point P, then f has a local maximum at P instead. So the pictures that are corresponding here, so this first picture is a picture of a local minimum. So again, we have a point at the bottom of the hill here. And if you think about it, to the left of that point, the first derivative is going to be negative because my function is decreasing. And to the right of that point, the first derivative is going to be positive because my function is increasing again. And the fact that the derivative is changing from negative to positive is exactly why I have a local minimum there. So this is one way to check to see if I have a local minimum. On the other hand, if we look at the graph next to it, here I have a local maximum. And to the left, f prime is greater than 0, and to the right, f prime is less than 0. And this captures the fact that I have a local maximum at that point x equals 0 in this case. All right, so here's an example of using the first derivative test to find local minima and maxima. So let's say that our function is x squared plus bx plus c. Well, if I want to use the first derivative test, I need to find the first derivative. And it is 2x plus b. And now I want to set that equal to 0 to find critical points. And this tells me that x is equal to negative b over 2. And this is the only critical point. So now I make a number line, put my critical point on it. And now I need to test, is the derivative negative or positive to the left and right of this critical point? That's what the first derivative test tells me to do. So to the left of that point, negative b over 2, I can check what is the derivative at negative b over 2 minus 1. So this would be one test point that you could use. And if you plug this in, it's not too hard to see that this is less than 0. And for a test point to the right, I could do negative b over 2 plus 1. And if you plug this in, this ends up being greater than 0. So we can take those question marks away. We have a negative to the left, we have a positive to the right. And so now we have to decide, is this a local minima or a local maxima at this point negative b over 2? Well, the function, or the derivative function, is going from negative to positive. So I know my function has to look something like this, and this is negative b over 2. So we have a local min at x equals negative b over 2. And I kind of already gave away the answer to the next part. If I want to sketch a graph of this function f, well, it's just going to look something like this. I have a single local minima at x equals negative b over 2. Okay, so that was the first derivative test. We have another option to determine whether a critical point is a local minimum or local maximum, and it's called the second derivative test. So in this case, again, we have a point P, which is a critical point. So f prime of P has to be equal to 0. And here's what we can do. So we can take the second derivative, and if the second derivative at that critical point P is greater than 0, then f has a local minimum at that point P. But if f double prime of P is less than 0, then f has a local maximum at P instead. And in this case, f double prime of P might end up being 0 again. And if that happens, then the test is inconclusive. So if you try and do the second derivative test, you work to get the second derivative, and then you plug in the point, you get 0, you're going to have to go back to square one and probably use the first derivative test instead. But most of the time, the second derivative test can save you a bunch of time. I think generally students like the second derivative test more than the first. Okay, so let's see if we can kind of make sense of what's going on here with the picture. In this first picture, I have my critical point P, and here I have a local minimum. So f prime of P is equal to 0. And let's see. So in this case, my function is concave up because the second derivative is greater than 0. And the fact that my function is concave up, again, if you think about it, is specifying that I must have a local minimum at that point P. And on the other side, again, f prime of P is equal to 0 at this local maximum. And this time, the second derivative is less than 0, and my function is concave down. And if you think about it, the fact that the function is concave down forces me to have a local maximum at that point P. Okay, so here's an example using the second derivative test. We have this function that we started with at the beginning, and I'll take the derivative again. It is 3x squared minus 18x minus 48, and I'll take the second derivative. It is 6x minus 18. And we found the critical points at the beginning. They were x equals 8 and x equals negative 2. And now we can use the second derivative test to determine whether these points are local minimums or local maximums. So we'll take those points and plug them into the second derivative. When I take x equals 8 and plug it in, I get something positive. And when I take x equals negative 2 and plug it in, I get something negative. So using the second derivative test, if the second derivative is positive, this means that my function is concave up. And so x equals 8 is a local min. And if my second derivative is negative, it means that my function is concave down. And x equals -2 is a local max. So again, this can be a little bit less work than the first derivative test because I can skip the number line game here. I can actually just take the critical points and plug them into the second derivative. Okay, I should say, just a warning for you, not every critical point has to be a local minimum or a local maximum. There are some critical points where if you look at the derivative to the left and the right, the derivative is not going to change sign. So if the derivative does not change sign from the left to the right, either negative to positive or positive to negative, then that point is not going to be a local minimum or a local maximum. So beware of that. And if you want to just check this for yourself, you can look at f of x equals x cubed and look at x equals 0. That's an example. Okay, last slide for us. Just one more example I want to show. A lot of times with derivatives and the way that they interact with functions and whether they're increasing, decreasing, concave up, concave down, a typical question that comes up is, can you sketch a curve given a certain amount of information? So here's an example of that kind of question. So let's see, we have a function f and it has the following properties. So f has critical points at x equals 2 and x equals 5. F prime of x is positive to the left of 2 and negative to the right of 5, and f prime of x is negative between 2 and 5. Okay, so let's see if we can sketch a possible function here. So I notice that I have special points at x equals 2 and x equals 5. So I'll kind of label them on the graph here. And f prime of x has to be positive to the left of 2 and negative to the right of 5. F prime of x is negative between 2 and 5. So my function has to be decreasing between 2 and 5. So I'm going to put 2 up there, and I'm going to put the point for x equals 5 down here. Okay, and f prime of x is positive to the left of 2. So I'm going to draw my function kind of like this. And I know the derivative has to be 0 at 2, so it's going to flatten out. And now as I'm going over to x equals 5, I have to be decreasing because f prime of x is negative. But I have to make sure that f prime at x equals 5 is 0 again, because I have a critical point there. And now let's see, we'll finish it off. Yeah, so if I look at the second one, f prime of x has to be negative to the right of 5. So once I get to 5, the function has to keep going down this way. Okay, and finally, identify the critical points as local maxima, local minima, or neither. So if I look at 2, I definitely have a local max at x equals 2. And this is because the derivative goes from positive to the left of 2, and it is negative to the right of 2. On the other hand, if I look at x equals 5, well, the derivative to the left of x equals 5 is negative, and the derivative to the right of x equals 5 is negative. So I have neither a local min nor a local max at x equals 5. So even though x equals 5 is a critical point, in this case it is not a local minimum or maximum because the derivative does not change sign when it goes through x equals 5. It's negative on the left and it's negative on the right. Okay, so hopefully this was a good introduction, an overview of what's going on in section 4.1. The homework for 4.1 is up on Wiley Plus, so feel free to start working on that.